In the grand silent theatre of the cosmos, the deadliest events are entirely invisible. They carry no sound, cast no shadow before their arrival, and offer no warning. They are the universe's perfect assassins' ghosts, born from the death of giants, and their passage is marked not by what is seen, but by what is erased. Imagine for a moment a world untroubled by such phantoms, a planet bathed in the gentle golden light of a stable star, orbiting within that precious razor-thin sliver of space we call the habitable zone. Its oceans a deep and vibrant sapphire churn with the chemistry of life, a cradle for beings of unimaginable form. Continents drift in a geological waltz, measured in eons, their surfaces painted with flora that breathe a strange alien air. Great crystalline mountain ranges scrape against a violet sky, their peaks shrouded in clouds of methane ice, catching the light of twin moons that chase each other across the celestial stage. On this world, life has found its footing. It has crawled from the primordial soup, conquered the land, and perhaps even looked up to its own sky with a dawning nascent curiosity. In the sprawling bioluminescent jungles that carpet its equator, complex ecosystems have woven themselves into an intricate tapestry of existence. Predators whose forms defy our terrestrial imagination stalk prey through forests of silicon-based trees that chime softly in the wind. Below the waves, entire civilizations of colonial organisms build shimmering organic cities on the ocean floor, their collective consciousness a slow, deliberate current in the deep. For 1 billion years, perhaps 2, this world has known nothing but the rhythm of its seasons and the slow, steady march of evolution. Its greatest dramas have been the rise and fall of dominant species, the patient sculpturing of canyons by water, the occasional impact of a wayward asteroid. Its inhabitants, whatever their intelligence, live with the profound unspoken assumption of continuity. They believe, as all life instinctively does, that tomorrow will be much like today. They are completely blissfully and fatally unaware that 65,000 light-years away in a forgotten corner of their own galaxy, a star has just died. It is not a gentle death. This is no graceful fading into a white dwarf or a quiet shedding of planetary nebulae. This is a titan, a star born with more than 40 times the mass of our own sun, a celestial behemoth that lived fast and furiously, burning through its nuclear fuel in a mere fraction of cosmic time. For millions of years it has been a raging furnace fusing heavier and heavier elements in its core, a desperate battle against its own colossal gravity. Now the battle is lost. The star's iron core, the final product of its fusion chain, can generate no more energy. In less than a second, the very heart of the star collapses under its own inconceivable weight. The core, once the size of a planet, crushes itself down into an object no larger than a city, an object so dense that a single spoonful would outweigh a mountain. A black hole is born in the star's dying breath, but the star does not simply vanish. The material just outside the newborn black hole, unable to escape its gravitational grip, is superheated to trillions of degrees and funneled into a swirling chaotic accretion disk. This is the universe's most violent engine. As the black hole spins, its immense rotational energy twists the surrounding magnetic fields into impossibly tight coils. For a fleeting moment, these fields act as a cosmic particle accelerator, a channel a rifle barrel aimed out across the galaxy. They seize a fraction of the dying star's energy and focus it into 2 opposing tightly collimated jets of matter and radiation erupting from the star's north and south poles. These jets, travelling at over 99.9% the speed of light, are the very definition of a gamma-ray burst. One of those jets, a focused beam of incandescent fury, just happens to be pointed directly at that tranquil violet-skied world. The warning, if you could call it that, travels at the speed of light. Which is to say, for the inhabitants of that distant world, there is no warning at all. There is no approaching rumble, no ominous celestial sign, no growing dread in the sky. There is only the instantaneous silent transition from existence to oblivion. One moment the world is alive, bathed in the familiar golden glow of its sun. The next, its sky is set on fire. The flash is not merely bright, it is a fundamental rewriting of reality. It is brighter than 1 trillion suns, a searing wave of high-energy photons, the most powerful form of light in the universe. This is the prompt emission, a torrent of gamma rays that slams into the planet's upper atmosphere. The delicate shield of ozone, painstakingly built over 1 billion years by microbial life, is not eroded or depleted. It is annihilated in less than a second, stripped away as the gamma rays shatter its molecules with brutal efficiency. The sky itself begins to burn. Nitrogen and oxygen, the inert, life-giving gases of the atmosphere, are torn apart and forcibly recombined into a toxic brown smog of nitrogen oxides. This newly forged chemical haze blankets the sunlit hemisphere, plunging the day into an eerie, poisonous twilight. For any living thing on that side of the planet, the end is mercifully quick. The sheer intensity of the radiation sterilizes the surface, boiling away the top layers of the oceans and flash-frying any organism caught in the open. The very air becomes a conduit for death, as the gamma rays create a cascade of secondary particles, a shower of muons and cosmic rays that penetrates deep into the ground and water, shredding the delicate molecular machinery of life. The light is so powerful it exerts a physical pressure, a photon wind that scours the landscape, a celestial blowtorch that melts rock and vaporizes forests. The world's surface is being pressure washed by pure energy, and still there is no sound. This apocalypse unfolds in a profound, magnificent silence, for the destruction travels faster than the speed of any shockwave. The beam itself is infinitesimally narrow on a galactic scale, perhaps only a few degrees wide, but for the world unfortunate enough to lie in its path, it is an all-encompassing catastrophe. The event lasts for perhaps 30 seconds. 30 seconds of unimaginable violence during which this single beam of energy outshines every other star in its galaxy combined. It releases more power than our own sun will generate over its entire 10 billion year lifespan, all focused into a searing cosmic needle. You could take the energy output of 1 billion trillion nuclear bombs, and you would still fall short of the power unleashed in these few moments. This is the awesome, terrible nature of a gamma-ray burst, or GRB. It is the most energetic, most luminous, and most violent phenomenon the universe has known since the Big Bang itself. It is not an explosion in the traditional sense, which radiates energy outward in all directions like a firecracker. A GRB is a targeted event. It is a focused demolition tool, a directed energy weapon wielded by the cosmos without malice or intent. The universe is not aiming, it simply is, and to be caught in the path of that beam is to lose the most unforgiving lottery in existence. For 65,000 years, this lethal volley of light has been crossing the interstellar void, a silent messenger of doom, its journey beginning long before the first glimmer of intelligence on that world even sparked into being. The star that fired the shot is long gone, its remnants a swirling nebula surrounding a new ravenous black hole. But its final posthumous act continues to travel outward, an echo of a tantrum so great it can sterilize a planet from halfway across the galaxy. The terror, however, is not confined to the 30-second blast. For those on the planet's night side, or those sheltered deep underground or in the oceans, the initial flash of gamma rays might not have been directly lethal. They would have been spared the instantaneous incineration. Their reprieve would be terrifyingly brief. They would emerge into a world irrevocably broken, a planet actively dying around them. The sky, now a permanent sickly brown shroud of nitrogen dioxide, blocks out the sunlight. Photosynthesis, the foundation of nearly every food chain, halts. The planet's green lungs collapse and the base of the ecological pyramid crumbles into dust. A new devastating rain begins to fall. The nitrogen oxides in the scorched atmosphere react with water vapour to form nitric acid, a corrosive downpour that poisons the land and acidifies the oceans on a global scale. Shell-building creatures dissolve plankton and die off in continent-spanning blooms of decay, and the water becomes a toxic soup. What the radiation didn't kill, the ensuing atmospheric and oceanic collapse will. This is a true mass extinction event, an environmental cataclysm so sudden and so total that evolution has no response. There is no adaptation, no hiding, no survival strategy. The planet's entire biosphere is being reset to zero. The damage extends even beyond the surface. The intense radiation has stripped the world of a significant portion of its atmosphere, thinning the protective blanket that shields it from the harshness of space. Cosmic rays, once deflected, now bombard the surface relentlessly, ensuring that any pockets of microbial life that might have survived deep underground are now subject to a steady sterilizing dose of radiation. The planet is now hostile to life on a fundamental chemical level. Over the coming weeks and months, the afterglow of the burst would arrive a slower wave of X-rays, ultraviolet and visible light, a fading echo of the main event. For any potential astronomers on that doomed world, it would be a final spectacular light show in their dying sky, the visible signature of the very weapon that had just executed their entire world. This is not a work of speculative fiction. This is not a fanciful horror story. This is physics. Gamma-ray bursts are real. We have seen them. Telescopes like the Swift Observatory and the Fermi Gamma-ray Space Telescope detect them happening somewhere in the distant universe almost every single day. We see them as fleeting, brilliant flashes of high-energy light from galaxies billions of light-years away, the cosmic death cries of stars in the young ancient universe. We chart their positions, we measure their unbelievable power, and we reconstruct the narrative of their birth in the heart of a hypernova, or in some cases the collision of two neutron stars, another cataclysm of equally terrifying proportions. Each detection is a chilling reminder of the raw, untamed power that courses through the cosmos. It confirms that the universe is not a placid, gentle garden, but a dynamic and often violent arena where the laws of physics can manifest as events of almost supernatural scale. We are separated from these distant cataclysms by an immense gulf of space and time, which renders them safe academic curiosities. They are fossils of light from a bygone era, their danger diluted by distance. But this raises the inescapable, deeply unsettling question. These events happen. They are a natural, albeit rare, part of the galactic life cycle. Stars far more massive than our Sun exist not just in distant galaxies, but here in our own celestial backyard, the Milky Way. What if one of those stellar titans, a ticking time bomb like Eta Carinae or Betelgeuse, were to collapse? What if its rotational axis, the barrel of its cosmic gun, happened to be aligned with our small, fragile blue planet? For us, there would be no 65,000-year journey. The flash would arrive in a geological eye blink. There would be no escape. The speed of light is the ultimate speed limit, and the instrument of our destruction would also be the messenger that announces it. You cannot outrun the light from the gun that is already firing at you. This is the ultimate cosmic threat, a danger so profound and so swift that it reframes our understanding of our own security in the universe. It forces us to confront the possibility that our continued existence depends on nothing more than a blind statistical fluke, the simple dumb luck of not being in the wrong place at the wrong time. The question then is not simply if it could happen, but what the true odds are. To find out, we must embark on a journey. We must hunt for these stellar monsters within our own galaxy, delve into the extreme physics that governs their explosive demise, and scour the Earth's own geological record for the faint, lingering chemical scars of past cosmic bombardments. We must become detectives in a cosmic cold case, searching for the fingerprints of a killer that can strike from halfway across the galaxy to determine if our world has ever stood in the path of a gamma-ray gun before, and what it would truly mean for us if it were to happen again. What does it take to keep the world from ending? In the shadowed corridors of the 1960s, at the absolute zenith of the Cold War, this was not a philosophical question. It was a terrifyingly practical problem, an equation of paranoia and physics that consumed nations. You lived under a fragile peace, a strange and terrifying equilibrium held in place by the promise of mutually assured destruction. The superpowers America and the Soviet Union faced each other across a geopolitical chessboard where the pieces were thermonuclear warheads. A single misstep, a single clandestine test of a new and terrible weapon could ignite the entire planet. To prevent this, to enforce the tenuous 1963 Partial Nuclear Test Ban Treaty, humanity looked to the heavens, not for salvation, but for sentinels. We needed spies in the sky, silent, unblinking witnesses posted in the unforgiving vacuum of space, watching for the one thing that could betray a secret nuclear detonation, a flash of light. But not just any light. We were hunting for the deadliest light in the universe, the high-energy shrapnel of a split atom. We were hunting for gamma rays. The program designed for this cosmic surveillance was codenamed Vela, from the Spanish verb for to watch. It was an elegant solution to a brutal problem. A constellation of satellites launched in pairs was placed into enormous orbits more than 100,000 kilometers high, far beyond the protective magnetic shield of our planet. From this godlike vantage point, they could see the entire globe at once. Each satellite was a marvel of miniaturization, a self-contained robotic spy bristling with detectors. Its sole purpose was to spot the characteristic signature of a nuclear bomb detonated in the atmosphere or in near space. This signature is a unique double-humped pulse of light. The first flash comes from the initial fireball of superheated air, an instantaneous burst of gamma rays and X-rays. The second, slightly later flash comes as the expanding shockwave reheats the atmosphere. Two flashes a fraction of a second apart. This was the specific damning fingerprint of a treaty violation. For years, these orbital guardians circled the Earth in a silent, lonely dance, waiting and finding nothing. The peace, it seemed, was holding. The system worked. And then on July the 2nd, 1967, an alarm went off. Deep inside the classified data centers at Los Alamos National Laboratory, a place born from the very physics of the atomic bomb, a signal arrived that made pulses race. Vela 4A and its sister satellite had seen something. A flash. A powerful, brilliant, unmistakable torrent of gamma rays. But as the analysts' men who had spent their careers studying the anatomy of nuclear explosions pored over the data, a profound sense of confusion began to creep in. The signal was all wrong. There was no telltale double pulse, no second hump of light. Instead, they saw a single, viciously sharp spike of energy that rose and fell in a matter of seconds, a profile unlike any weapon they had ever conceived. It was a celestial scream with no echo. Immediately, the gears of national security began to grind. Had the Soviets developed a new kind of weapon, something that could bypass our detection systems? Was it a malfunction? A cosmic ray striking a sensor in just the right or wrong way to mimic a genuine event? The team led by physicist Ray Klebsadel ran through every possibility with painstaking diligence. They checked the satellite's health, the telemetry, the background radiation levels. Everything was nominal. This was not an error. This was a real event. Their next task was to find out where it came from. The Vela satellites were not just detectors, they were a network. By measuring the infinitesimally small difference in the signal's arrival time at each satellite, a delay measured in milliseconds, they could triangulate the source just as you can pinpoint the location of a thunderclap by hearing it from different positions. They ran the calculations expecting the vector to point towards a known Soviet test site, or perhaps a suspicious blank spot on the map. The answer that came back from the stark logic of the computers was deeply unsettling. The flash hadn't come from the Soviet Union. It hadn't come from anywhere on Earth at all. In fact, it hadn't even come from our own solar system. The directional data was unambiguous. The source was somewhere out there in the fathomless silent depths of interstellar space. Imagine the quiet tension in that room. You're a scientist tasked with preventing nuclear war, and your instruments, the most sophisticated watchdogs ever built, are telling you that a mysterious, unimaginably powerful explosion has just occurred in the cosmos. You cannot tell your astronomical colleagues. The entire Vela program is top secret. The data is classified at the highest levels. You are sitting on one of a monumental discovery, a completely new and violent astrophysical phenomenon, but you can't breathe a word of it. Your job is to look for bombs, not for celestial wonders. So you file the report, mark it as unexplained, and you wait. The weeks turn into months, and then it happens again. Another burst, just as brief, just as powerful, from a completely different direction in the sky. Then another, and another. Over the next few years, a secret catalogue of these phantom events began to grow within the classified archives of Los Alamos. 16 events by 1973. Each one a ghost in the machine, a cosmic enigma captured by a nuclear surveillance network. They were like messages in a bottle from an unknown violent ocean, and only a handful of people in the world even knew they were washing ashore. For 6 long years, this profound cosmic secret was held by the United States military. The analysts, led by Klebsadel, Ian Strong and Roy Olson, became the sole gatekeepers of this new window onto the universe. They meticulously catalogued each event, refining their triangulation methods, confirming again and again that these were not homegrown threats. They were blasts of energy originating from truly random points on the celestial sphere. They weren't clustered along the plane of the Milky Way where the stars of our own galaxy reside. They weren't concentrated around nearby galaxies like Andromeda. They appeared everywhere like holes punched in the fabric of the sky from some unseen dimension. This randomness was itself a clue of immense significance. It suggested one of two staggering possibilities. Either these events were happening very close by, in a sort of halo around our own solar system, or they were happening unfathomably far away, in the distant voids between galaxies at what astronomers call cosmological distances. If they were close, they were strange. If they were far, they were impossible. The amount of energy required for a blast to appear so bright from halfway across the observable universe was simply mind-boggling, a figure that broke the known laws of physics as they were understood at the time. Finally, by 1973, the military was thoroughly convinced that these gamma-ray flashes were of natural astrophysical origin. They posed no threat to national security. The secret had been kept long enough. Kleber Sardell and his team were given permission to publish their findings. And so, in an understated paper in the Astrophysical Journal, the world of astronomy was formally introduced to the things we now call gamma-ray bursts, or GRBs. The reaction was a mixture of stunned disbelief and sheer excitement. Here was a phenomenon that dwarfed anything humanity had ever witnessed. In the space of a few seconds, a single GRB could release more energy than our own sun will produce in its entire 10 billion year lifetime. Think about that for a moment. All the light, all the heat, all the raw power poured out by our star over its whole existence compressed into a fleeting moment, a cosmic flashbulb going off in a distant galaxy. And we had found them completely by accident using spy satellites designed to look for something else entirely. It was as if you had built a security camera to watch for burglars in your backyard, only to discover it was recording the birth of new universes on the other side of town. The discovery threw open the doors to 1,000 new questions and ignited one of the most ferocious debates in the history of modern astronomy. With no visible counterpart, no exploding star, no colliding galaxies at the source, the bursts were completely invisible to traditional telescopes that see in optical light. They were phantoms existing only in the gamma-ray spectrum for a few fleeting seconds, before vanishing forever. All we had were these brief violent squiggles on a data plot. The central mystery, the one that cleaved the scientific community in two for the next 20 years, was the question of distance. It became known as the Great Debate. On one side, you had the galactic model proponents. They argued that these bursts must be occurring within our own Milky Way. Perhaps they were eruptions on the surface of nearby neutron stars, the collapsed city-sized corpses of massive stars. In this model, the events were still incredibly powerful, but manageable. They were local tempests in our own cosmic neighbourhood, requiring exotic but not physics-shattering amounts of energy. It was the conservative logical position. On the other side were the proponents of the cosmological model. They took the random distribution of the bursts across the sky at face value, and made a bolder claim these were not local phenomena. They were the most powerful explosions in the universe since the Big Bang itself, occurring in galaxies billions of light-years away. For us to even see them from such a colossal distance, the energy released had to be almost beyond conception. This idea was considered by many to be wildly speculative, even reckless. There was simply no known physical mechanism that could generate such an outrageous amount of power. It would be like suggesting a firecracker could outshine the sun. The debate was not merely academic. It touched upon the very limits of our understanding of matter, energy, space, and time. What kind of celestial engine, what sort of cosmic monster could possibly power such a cataclysm? Theories began to fly, each more exotic than the last. Were they the result of two neutron stars locked in a death spiral for eons, finally crashing together and merging into a black hole? Were they a new terrifying breed of supernova, a hypernova that occurred when the most massive stars in the universe collapsed at the end of their lives? The problem was a maddening lack of data. Catching a GRB was pure luck. They were ephemeral, unpredictable. You couldn't point a telescope at a spot in the sky and wait for one to go off. By the time you detected the gamma rays and swiveled your other instruments to that location, the show was long over. It was like trying to photograph a lightning strike by only pointing your camera after you hear the thunder. For years, progress stalled. We knew the universe was a shooting gallery, but we were blindfolded, only able to hear the shots after they were fired. We needed new eyes. We needed dedicated observatories in space designed not to look for clandestine nuclear tests, but to scan the entire sky, day and night, for these specific cosmic apparitions. The first generations of these true GRB hunters were launched satellites with names like Uhuru and the Compton Gamma Ray Observatory. They were a direct legacy of the Cold War instruments of science born from instruments of war. Their mission was to gather more data points to find more of these bursts to build up a better map of their locations, in the desperate hope of finding a pattern, any pattern that could help solve the maddening riddle of their distance and their origin. The early results only deepened the mystery. The new, more sensitive detectors found that GRBs were happening constantly at a rate of about one per day somewhere in the observable universe. They confirmed the utter randomness of their locations. There was no hint of a concentration along the disk of the Milky Way, which would have been the smoking gun for the galactic model. The evidence was slowly, painstakingly beginning to tilt towards the cosmological camp, towards the more terrifying and awe-inspiring conclusion. If they were right, if these flashes truly were coming from the edge of the visible cosmos, then we were living in a universe far more violent and unpredictable than we had ever dared to imagine. It meant that the faint seconds-long bursts of gamma rays being collected by our satellites were the distant echoes of events of almost unimaginable fury. They were the death cries of stars in galaxies so far away that the light from the explosion had been travelling towards us for billions of years, since before the Earth itself had even formed. And so the stage was set. A secret discovery born from the nuclear paranoia of the Cold War had blossomed into one of the greatest astrophysical quests of our time. We had stumbled upon the calling card of a cosmic monster, but we had no idea what it looked like, where it lived, or how it worked. We had detected its power, but we could not comprehend its source. We were like ancient people huddled around a campfire, seeing the flicker of a distant, impossibly bright volcano on the horizon, and wondering what kind of god could possibly be so angry. The journey from that first perplexing signal in 1967 had led us to the precipice of a new cosmology, one where the quiet, empty spaces between galaxies were punctuated by explosions that could in a matter of seconds outshine all the stars in the universe combined. The great debate was still raging, the evidence was still circumstantial, and the ultimate truth remained tantalizingly out of reach. To solve it, we would need a breakthrough. We would need to find a way not just to see the flash, but to see its aftermath, the cooling, fading embers of the fire itself. We would need to catch a gamma-ray burst in the act. So the ghosts remained flickering at the edge of perception, their existence an undeniable yet maddeningly incomplete truth. For decades we knew these gamma-ray bursts were real thanks to the vigilant eyes of satellites built to watch for terrestrial threats. But that knowledge was a hollow victory. We were like detectives at a crime scene with no body, no weapon, and no location, just the echo of a gunshot ringing in our ears. The scientific community, starved of data, had fractured into two fiercely opposing camps, their debate echoing through the halls of astronomy. One faction, cautious and grounded, argued for a local origin. They proposed the bursts were the death cries of exotic objects like neutron stars hiding within the vast spherical halo of our own Milky Way galaxy. This was a comfortable, manageable theory. It kept the monsters in our own backyard frightening but at least comprehensible in their energy demands. The other camp, more audacious and perhaps more imaginative, dared to suggest something far more profound. They saw the bursts not as local phenomena, but as cataclysms from the deepest chasms of space events taking place in galaxies billions of light years away. To the localists, this was sheer fantasy. For a burst to be visible from such a mind-shattering distance, it would need to release an amount of energy that defied all known physics and output so titanic it would momentarily outshine the rest of the entire observable universe combined. The idea was preposterous and offence to astrophysical reason. Without a map, without any sense of their distribution in the sky, the argument was a stalemate, a war of words fought in the dark. What we needed was a new eye, a purpose-built sentinel with a gaze wide enough to watch the entire sky at once. We needed a cartographer for these phantoms, and in the spring of 1991 humanity launched one. Rising from the Earth on the back of the space shuttle Atlantis was a 17-ton titan of astronomy, the Compton Gamma Ray Observatory, It was the most ambitious, most sensitive gamma-ray telescope ever conceived, a marvel of engineering designed to peel back the most violent and energetic veil of the cosmos, and tucked onto its massive frame was an instrument that would change everything. It was called the Burst and Transient Source Experiment, or BATSI. It wasn't a telescope in the traditional sense. You couldn't point it and take a picture. Instead, BATSI was an ingenious, almost brutalist piece of hardware. It consisted of 8 detector modules, sodium iodide crystals that would scintillate or flash when struck by a high-energy photon. These 8 detectors were arranged on the corners of the observatory, like the faces of a colossal 8-sided die cast into the heavens. Each detector pointed in a different direction, collectively giving BATSI an uninterrupted panoramic view of the entire celestial sphere. When a gamma-ray burst erupted anywhere in the sky, it wouldn't hit all 8 detectors with the same intensity. The detectors facing the burst would receive a torrent of photons lighting up furiously. Those on the opposite side, shielded by the bulk of the spacecraft, would see far fewer or none at all. By comparing the relative brightness of the flash across its 8 different eyes, BATSI could perform a crude form of triangulation. It couldn't pinpoint the source with the accuracy of a sniper, but it could identify a general patch of sky where the burst had originated, an error box that was still frustratingly large, but for the first time, it gave us a place to look. The great mapping had begun. Day after day, week after week, the vigil continued in the silent orbit above Earth. And the bursts came, one every day or 2 on average. Each time an alarm would sound in the control rooms on the ground, a torrent of data would pour down, and the team at NASA's Marshall Space Flight Center would get to work. They would analyze the signal, its duration, its chaotic energy profile, and most importantly, the information from the 8 detectors that told them where it had come from. On a blank map of the sky, a new dot would appear. At first, it was just a scattershot of points, a random peppering with no discernible form. The tension was palpable. The entire debate, the entire future of high-energy astrophysics, rested on the pattern that would eventually emerge from this cosmic pointillism. Would the dots begin to trace a familiar shape? If the local model was correct, if the bursts were coming from our own galactic halo, then the map should eventually reveal the presence of our galaxy's central hub, the great bulge of stars and gas at its core. The Andromeda Galaxy, our nearest major neighbour, should also appear as a faint cluster of points. We would expect to see a concentration of bursts, a subtle preference for certain directions. But as the month turned into a year, and the number of detected bursts climbed into the hundreds, a strange and unnerving picture began to take shape. The dots were not clustering. They were not tracing the glowing band of the Milky Way that stretches across our night sky. They were not favouring any constellation, any direction, any hemisphere. They were coming from everywhere. With each new detection, the evidence became more damning, the conclusion more inescapable. The map that BATSI was painting was one of perfect statistical uniformity. It was a spray of cosmic buckshot across the entire celestial sphere. This property, known as isotropy, was the single most important clue we had ever uncovered, and its implications were staggering. Think of what the sky looks like from your vantage point. If you were in a forest, you would see trees in every direction. But if you were in a city, you would see tall buildings clustered in the downtown core and smaller buildings spreading out into the suburbs. Our galaxy is like that city. We live in its suburbs. If the GRBs were happening inside our city, we would expect to see most of them coming from the direction of its dense, chaotic downtown, the galactic plane, and the galactic center. The fact that we saw them equally in all directions meant one of 2 things. Either we were in the exact geometric center of a vast spherical shell of burst-producing objects surrounding our solar system, a proposition so egocentric and unlikely it borders on the absurd, or the bursts were happening on a scale so immense, so truly cosmic, that our entire Milky Way galaxy was just one insignificant point of view. It meant the bursts were not in our galaxy, or even in our local group of galaxies. They were cosmological. They were coming from the edge of the visible universe. The audacious, seemingly ludicrous theory was correct, and with that revelation a profound sense of awe mingled with a new and chilling terror. The energy problem was no longer a theoretical objection. It was now a horrifying reality we had to confront. Let's try to grasp the scale of this violence, a scale that threatens to shatter our very language. Imagine the entire energy output of our sun over its full 10 billion year lifespan. All the light, all the heat, all the radiation it will ever produce from its birth to its death. Now imagine taking all of that energy and compressing it. Not into a year, not into a day, but into a single fleeting moment, lasting from a few milliseconds to a couple of minutes. That is the power of a single gamma ray burst. From its location billions of light years away, a GRB unleashes a focused torrent of energy, so potent that for a brief terrible instant, it can outshine its own host galaxy by a factor of millions. It is an announcement of power so absolute, it bordered on the divine or the demonic. It was a form of stellar death for which we had no name and engine of destruction beyond our wildest nightmares. The discovery that GRBs were cosmological didn't solve the mystery. It plunged it into a far deeper and more terrifying abyss. We had found the monsters, and they were not in our backyard. They were everywhere, inhabiting the grand cosmic ocean, and their roars were the most powerful sounds in the universe. But even with this knowledge, we were still staring at shadows. BeppoSAX could tell us that a burst happened and roughly where, but its error boxes were still enormous. By the time astronomers on the ground could point their powerful optical telescopes to that patch of sky, hours or days had passed. The burst was long gone, the fire was out, the scene was cold. It was like hearing a scream from a specific city block, but arriving to find the streets empty with no clue as to which building it came from. Without a precise location, we could never find the source, never identify the host galaxy, never truly understand what kind of celestial object was capable of such catastrophic violence. We were stuck staring at a map of cosmic crime scenes with no hope of ever finding the culprit. A new strategy was needed. We didn't just need to see the initial flash of gamma rays, we needed to be able to catch the fading, dying ember of the explosion in its aftermath. This lingering cooling emission, what theorists predicted would be an afterglow, should be visible at longer, less energetic wavelengths like X-rays, visible light, and radio waves. Finding it was the key, but it required a spacecraft with a unique combination of abilities, a wide-field eye to catch the initial unpredictable burst, and a nimble, fast-reacting telescope that could within minutes swivel and zoom in on the location with pinpoint accuracy. The world of astrophysics held its breath waiting for such a machine. It arrived in 1996, an Italian-Dutch collaboration with a beautifully fitting name, BeppoSAX, named after the Italian physicist Giuseppe Beppo Occhialini. BeppoSAX was not as large or as sensitive as Compton in its gamma-ray detectors, but it possessed something far more critical for this next phase of the investigation: agility. It was a hunter built for the chase. Its wide-field cameras would watch the sky, and the moment a GRB was detected, the spacecraft's onboard computer would calculate the position and autonomously command the entire satellite to pivot, pointing its narrow-field X-ray telescopes directly at the source. This entire sequence had to happen in minutes before the precious fading signal vanished completely. It was an audacious gamble. For months after its launch, BeppoSAX watched and waited. It saw bursts, but none were bright enough or positioned correctly for the rapid follow-up. The frustration grew. Had they designed the mission correctly? Was the afterglow even real, or just a figment of theorists' imaginations? Then, on February 28, 1997, it happened. A moderately bright burst designated GRB 970228 triggered the detectors. Onboard, the software sprang to life. Thrusters fired. The satellite, weighing over a ton, gracefully slewed across its orbital path. 8 hours later, a delay caused by the source's position relative to the Earth, the X-ray telescopes began their observation of the now empty patch of sky. And there it was. Exactly where the burst had been, the sensitive X-ray eye of BeppoSAX saw a faint fading point of light. It was the afterglow. For the first time in human history, we were not just seeing the brilliant chaotic shout of the explosion, but the dimming mournful echo. The smoking gun had been found. The discovery was electric, sending shockwaves through the astronomical community. The coordinates from the X-ray detection were orders of magnitude more precise than anything BeppoSAX could ever provide. They were immediately broadcast to observatories across the globe. On the island of La Palma, astronomer Jan van Paradise and his team turned the William Herschel telescope toward that exact spot in the constellation of Orion. And as the image resolved on their screen, they saw it a tiny faint smudge of light, a point source that had not been there in previous surveys of that same patch of sky. They were looking at the first ever optical afterglow of a gamma-ray burst. They watched it over the next few days, and just as the X-ray source had done, this tiny pinprick of visible light began to fade, disappearing back into the blackness from which it came. This was the moment that changed everything. The ghostly footprint was no longer ghostly. It was real, tangible light that we could capture, measure, and analyze. This was more than just a confirmation. It was the key that would unlock the final door. Because now that we had a precise location and a visible source, we could perform the most powerful measurement in all of cosmology. We could take its spectrum. By passing the faint light of the afterglow and its host object through a spectrograph, astronomers could see how much its light had been stretched by the expansion of the universe. This stretching, this cosmic redshift, is the ultimate yardstick. It doesn't just tell you if something is far away, it tells you how far. A few months later, another burst GRB 9/0508 was pinpointed by BeppoSAX. This time the follow-up was even faster. Telescopes at Kitt Peak and the mighty Keck Observatory in Hawaii locked onto the afterglow. They measured the light and the data came back clear and unambiguous. The redshift was 0.835. This number, so simple and clinical, was a final declarative statement. It corresponded to a distance of some 6 billion light-years. It meant the light from this explosion had travelled for 6 billion years to reach us, a journey that began long before our own planet had even formed. The debate was over. It was not a theory. It was not a model. It was a measured physical fact. Gamma-ray bursts were definitively, undeniably cosmological. They were the most luminous explosions in the universe, ancient beacons from a younger, more violent cosmos. The work of Compton and BeppoSAX had shown us the grand pattern, the isotropy that pointed to the far-off heavens. But it was the nimble grace of BeppoSAX and the tireless work of ground-based astronomers that finally took us to one of those distant addresses, letting us read the mail and confirm once and for all just how far away from home we truly were. The mystery of their location was solved, but in solving one puzzle, we had created a monster of another. We now knew with certainty that these events possessed an energy that beggared belief, a power that seemed to violate the very laws of nature as we understood them. The battle for where was over. A much more terrifying war, the war for what, was about to begin. For decades, the light from these cosmic phantoms arrived with a bewildering lack of context. They were isolated cries in the electromagnetic dark, their true nature cloaked in the sheer, unimaginable distances from which they came. But as our catalogues swelled, as the Compton Gamma-Ray Observatory dutifully logged thousands of these unearthly blasts, a deep and unsettling pattern began to emerge from the static. Buried within the data, within the plots of brightness and time, was a schism, a fundamental division that hinted at something we had completely failed to appreciate. We were not hunting a single monster. We were hunting two. The clue was elegantly, deceptively simple. It was all about time. When astronomers plotted the duration of every burst they had ever seen, the results were not a smooth curve, a single bell shape representing one kind of event. Instead, the graph split, showing two distinct populations clustered around two different timescales. There was a large dominant group of bursts whose gamma-ray fireworks lasted longer than 2 seconds, sometimes stretching on for agonizing minutes of celestial violence. And then there was another more elusive family. These were fleeting, impossibly brief apparitions lasting less than 2 seconds, often just a few tenths of a second. A cosmic flashbulb popping off in the void. This discovery was the Rosetta Stone for gamma-ray bursts. It was the moment the unified mystery fractured into a dual-fronted investigation. It told us in the stark language of data that the universe had conceived of at least two entirely different ways to generate the most powerful explosions it could muster. The long bursts and the short bursts, two classes of cataclysm, two different cosmic engines of annihilation, each requiring its own unique and terrifying explanation. The question was no longer simply, what is a gamma ray burst? Now it was, what are they? And solving the puzzle of the more common long-duration bursts would require us to imagine the death of a star so extreme, so violent, it would rewrite the very definition of a supernova. The answer began to coalesce around a single extraordinary idea. A model of stellar death so complete and so audacious, it felt like something torn from mythology. It was called the collapsar model, and it demanded we journey deep inside the heart of a true cosmic behemoth, a star at the absolute upper limit of existence. Forget a star like our Sun. You must picture a giant, a true leviathan of the cosmos, perhaps 40, 50, or even 100 times more massive. This is a star that has lived its life in the fast lane, burning through its nuclear fuel with profligate fury. In its final days, powerful stellar winds have stripped away its outer puffy layers of hydrogen and helium, leaving behind a dense, exposed core of heavier elements. This is a Wolf-Rayet star, a ticking time bomb of unimaginable proportions. But even its immense mass is not the most crucial ingredient. The secret, the absolute key to unlocking the gamma-ray burst is rotation. This star must be spinning and spinning incredibly fast. It is a gravitational gyroscope, a whirling dervish of superheated plasma, the size of an orbit containing all the kinetic energy needed for the approaching apocalypse. For millions of years, the outward pressure of nuclear fusion in its core has held the crushing force of its own gravity at bay. A delicate, ferocious balance. But now the fuel is gone. In a single, silent moment deep within the star, the furnace goes out. The balance is broken. And gravity, the patient, relentless force of the cosmos, finally wins. There is nothing left to stop it. The core, an object already packing more mass than our Sun, into a volume smaller than the Earth, begins to collapse. It is a freefall on a scale that defies comprehension. In less than a second, the stellar core plummets inward, crushed by the weight of the star above it, accelerating to over a quarter of the speed of light. The temperatures and densities skyrocket to levels unseen since the Big Bang. The core compacts so violently that protons and electrons are fused together into a sea of pure neutrons. For a moment it seems a neutron star might be born. But for a star this massive, this is only a momentary pause. The neutron star itself is overwhelmed. The crush of gravity is absolute. And in that final infinitesimal moment of collapse, something new is born in the heart of the dying star, a black hole. A point of infinite density, a brand new rupture in the fabric of space-time now sits silently, where the star's engine once roared. Yet the rest of the star, its vast layered shell of carbon, oxygen and silicon, is still falling inward, unaware that its core has been replaced by an abyss. But because the original star was spinning so rapidly, this infalling material cannot plummet directly into the black hole's maw. Instead, angular momentum takes over. The stellar guts are whipped into a frenzy, forming a swirling, hyperdense, magnetically charged vortex around the newborn black hole. This is the accretion disk, not the kind we see around distant quasars, but a temporary savage engine forged from the star's own substance, heated to trillions of degrees. It is a maelstrom of unimaginable power, dumping the mass of several suns into the black hole every single second. It is this combination, the spinning black hole and its ravenous supercharged accretion disk, that forms the central engine of the gamma-ray burst. The extreme rotation of the black hole itself twists the magnetic fields embedded within the disk, winding them up like a colossal cosmic spring. The forces at play are beyond anything we can replicate or even truly model, and then at a critical breaking point that stored energy is unleashed. From the poles of the black hole, two opposing tightly focused jets of material are launched outward. These are not mere explosions, they are celestial blowtorches of almost pure energy. Particles are accelerated to 99.9999% of the speed of light, a velocity so extreme that time for them slows to a crawl. But these jets are still buried deep inside the collapsing star. They are a weapon fired from within a mountain. To become a gamma-ray burst, they must first escape. What follows is a desperate, violent race. The jets, narrower than a laser beam on a cosmic scale, begin to punch their way through the collapsing outer layers of the star. It is a journey through a chaotic, dense environment of stellar debris. This titanic struggle takes time, seconds, sometimes minutes. The jet pushes and superheats the material in its path, carving a tunnel out of the very star that created it. And all the while, the black hole at the centre continues to feed, powering the jets with a relentless fury. Finally, the jet breaks through. It erupts from the surface of the dying star and blasts out into the vacuum of space. Only now, free from its stellar prison, can it generate the light we see. The material within the jet itself is not smooth. It is clumpy and turbulent, with faster shells of matter catching up to and slamming into slower ones. These internal collisions, occurring at nearly the speed of light, create a series of brilliant shock waves. It is within these shocks that particles are accelerated and magnetic fields are amplified, forcing electrons to radiate away their energy as a blinding, focused flash of high-energy gamma rays. This is the initial brilliant scream of the burst, the prompt emission, that our telescopes detect from across the universe. The duration of this scream corresponds directly to how long the central engine, the black hole and its disk remains active, and how long it takes the jet to escape its stellar cocoon. This perfectly explains the timescale of the long bursts. The collapsar model was no longer just a theory. It made a powerful prediction that these bursts should be found in regions of space where massive young stars are born and die quickly. And when we finally managed to pinpoint the fading afterglows of long GRBs, that is exactly where we found them, nestled inside the bright star-forming arms of distant spiral galaxies. The theory had found its proof written in the starlight of dying cities of suns. We had solved one half of the mystery. The anatomy of the long bursts these hypernovae was laid bare. But this success only deepened the enigma of their cousins, the short bursts, the fleeting ghostly flashes that lasted less than 2 seconds. They were different. Their gamma rays were on average even more energetic, carrying a harder spectral signature. And for years they remained phantoms. We could not capture their afterglows. We could not find their homes. They seemed to happen nowhere in particular, sometimes appearing in the empty dark halos of galaxies, where star formation had ceased billions of years ago. A massive collapsing star simply didn't fit. You do not find Wolf-Rayet stars which live for only a few million years in ancient stellar graveyards. The engine for the short bursts had to be something else entirely. Something older. Something smaller. And something, if it were even possible, more violent. The answer astronomers began to suspect lay not in the death of a single isolated star, but in the final destructive embrace of a pair of the most extreme objects in the universe. We had to imagine a binary system, 2 stellar corpses locked in a gravitational death dance. We had to imagine the collision of neutron stars, picture a scene set in the silent emptiness of intergalactic space. 2 objects each no larger than a city are orbiting each other. But these are not planets. They are the collapsed cores of stars that exploded in supernovae long ago. They are neutron stars. Each one contains more mass than our Sun, crushed into a sphere of pure nuclear matter so dense a single spoonful would outweigh Mount Everest. For eons, perhaps billions of years, they have been locked in this binary waltz, but their dance is not eternal. According to Einstein's theory of general relativity, these orbiting accelerating masses are constantly churning the fabric of space-time around them, radiating away their orbital energy in the form of invisible ripples, gravitational waves. This loss of energy is minuscule, but it is relentless, and it causes their orbit to decay. Slowly, imperceptibly at first, then faster and faster they begin to spiral inward. They are doomed. In their final minutes, they are whirling around each other hundreds of times per second, moving at a significant fraction of the speed of light. The gravitational radiation they are emitting becomes a powerful shriek, warping and twisting space-time in their immediate vicinity. The tidal forces are titanic. The neutron stars, these perfect spheres of unimaginable density, begin to deform. Their crusts shatter, ripping apart under gravitational stresses that would vaporize any normal matter, and then they touch. The collision is an event of such extremity that our language and physics struggle to describe it. This is not matter hitting matter in any conventional sense. This is a merger of 2 objects already at the brink of physical law. In a few thousandths of a second, the two neutron stars tear each other to shreds, erupting into a swirling vortex of superheated neutron-rich debris. At the centre of this cataclysm, one of two things happens. Either the combined mass forms a monstrous, hypermassive neutron star that survives for a mere millisecond before collapsing under its own weight, or more likely the merger triggers the immediate formation of a black hole. Just as in the collapsar model, a spinning black hole is born surrounded by a temporary ferociously hot accretion disk. But this disk is not made of familiar stellar plasma. It is forged from the raw exotic material of neutron stars. Once again, this central engine, the black hole and its nuclear density torus, launches twin tightly collimated jets of energy and matter roaring outward at nearly the speed of light. But here is the crucial difference. There is no star to escape from. The jets erupt directly from the merger site into the near-perfect vacuum of space. There is no stellar cocoon to burrow through, no dense layers to impede their progress. The entire process, from collision to jet launch, to the production of gamma rays through internal shocks, happens in a blinding flash. The central engine lives and dies in less than 2 seconds. The model was a perfect fit. It explained the short duration. It explained the harder, more energetic gamma rays born from a more compact and even more extreme environment. And it explained their mysterious locations. Binary neutron star systems are ancient. They can survive for billions of years before they finally merge. During that time, the initial supernova kicks that created them can send them hurtling out of their host galaxy. They can drift for eons through the desolate void only to finally merge and explode in the loneliest corners of the cosmos, far from any stellar nursery. For years, this remained the leading, most compelling hypothesis, a beautiful theory awaiting its definitive proof. That proof would arrive in a way more spectacular than anyone had dared to dream, not just as a flash of light, but as a vibration in the fabric of reality itself. The discovery of these two distinct pathways to cosmic annihilation was a watershed moment. It transformed the study of gamma-ray bursts from a singular obsession into a complex, rich field of cosmic forensics. We had identified the culprits. For the long lingering cries of the gamma-ray light, the murderer was a massive spinning star committing suicide and giving birth to a black hole in its heart. For the short, sharp shrieks, the culprits were a pair of stellar zombies, the dense neutron star remnants of stars long dead, colliding in a final gravitational apocalypse. The universe, it turned out, was profoundly creative in its methods of destruction. But in solving this great mystery, we had uncovered an even deeper one. These events weren't just about destruction. In the heart of these cataclysms, in the fire of these mergers and collapses, something else was happening. These cosmic forges were not just engines of death. They were also engines of creation, seeding the cosmos with the very elements that make life and planets possible. The gold in your ring, the platinum in our electronics. Their story did not begin in the heart of an ordinary star. Their story began here in the final violent second of a gamma-ray burst. We have stared directly into the abyss, into the heart of the universe's most violent acts. We've witnessed the death throes of a star 100 times the mass of our sun collapsing under its own colossal weight. We've seen the ghosts of stars, the neutronium cinders of a supernova locked in a gravitational death spiral, shredding each other into a fountain of pure energy. We have identified the engines of annihilation, but understanding what pulls the trigger is a profoundly different and perhaps more comforting question than the one we must now ask: where is the barrel of the gun pointed? Because the true soul-chilling horror of a gamma-ray burst lies not in its explosive power, which is nearly beyond comprehension, but in its terrifying, focused and inescapable precision. An explosion like the supernovae that seed the cosmos with the elements of life is a generous catastrophe. It throws its energy and matter outwards in all directions, a spherical wave of creation and destruction that expands and dilutes with distance. It is an act of cosmic democracy. Everyone in the neighbourhood gets a share of the fallout. A gamma-ray burst, however, is a cosmic tyrant. It is not an explosion in the way we imagine it. It is an execution. The unfathomable energy from the dying star or the merging stellar remnants isn't cast out into the void indiscriminately. Instead, the maelstrom of the central engine with its hyper-compressed matter and impossibly twisted magnetic fields acts as a colossal particle accelerator, a gravitational nozzle of unimaginable power. It takes the raw fury of 100 supernovas and funnels it focuses, it collimates it into two narrow opposing jets of energy and matter. These jets, these celestial blowtorches, erupt from the poles of the dying system, punching clean through any stellar debris that stands in their way. They travel outwards at more than 99.9% of the speed of light. Think of it this way: a supernova is a bomb, a gamma ray burst is a bullet. Burst. A very, very large bullet moving at the speed of thought fired from a gun the size of a solar system. This is the great paradox of the gamma ray burst. This very beaming effect is what makes them appear so rare. For every one we see, there could be 500 others erupting across the universe, their barrels pointed away from us, their lethal beams slicing harmlessly through empty space. We are only ever aware of the ones that are aimed by pure random chance directly at our front door. This focusing mechanism means you don't have to be near a GRB to be in mortal danger. You just have to be in the wrong place at the wrong time. Across thousands, even tens of thousands of light years, the beam remains lethally concentrated. Its power barely diminishes. It travels across the galaxy not as an expanding wave, but as a tight, coherent needle of pure annihilation, a cosmic sniper shot fired millennia before its target is even aware the trigger has been pulled. So let us place ourselves in the path of this phantom menace. Imagine, if you will, a world much like our own. A vibrant living planet orbiting a stable star brimming with the complex and fragile chemistry of life. It has oceans and continents, an atmosphere rich with oxygen and a protective magnetic field. Its inhabitants, whatever they may be, go about their lives under the comforting illusion of celestial permanence. Then, from a distance of 6,000 light-years, a colossal star in a distant spiral arm finally exhausts its fuel. Its core collapses, the jets ignite, and one of them, by the merciless lottery of cosmic alignment, is now pointing directly at this unsuspecting world. For 6,000 years, the beam of death travels crossing the interstellar void in silence. On the target world, empires might rise and fall. Species may evolve and vanish. Continents may drift. The sky above remains a tapestry of serene, predictable lights. There is no warning. No approaching shadow. No harbinger of doom. The weapon is travelling at the speed of light. The flash of the muzzle and the impact of the bullet are for all intents and purposes the very same event. The first indication that anything is wrong is the sky itself catching fire. This is the prompt emission, the gamma ray pulse. For anywhere between a few milliseconds and a terrifying couple of minutes, the daylit side of the planet is bathed in a torrent of high-energy photons. This is not light that warms, it is light that shreds. The energy flux is staggering. In these few seconds, the surface of the planet is hit with more raw energy than if a 1 megaton nuclear bomb were detonated every square kilometre across the entire hemisphere. Life on the surface exposed to the sky is vaporized. Not burned, not killed in a biological sense, but fundamentally disassembled at a molecular level. The intricate bonds of organic chemistry are shattered instantly. The oceans would flash boil at the surface, a steam explosion that would dwarf any terrestrial volcanic eruption. The very air would be ionized, glowing with a ghastly silent luminescence. For any creature with eyes to see the sky, would become a wall of white blinding light, the last thing it would ever perceive. This initial wave is a sterilizing pulse of almost perfect efficiency. But it is only the opening salvo. The true planetary destruction has barely begun. The gamma rays themselves are only the first ghost in the machine. As this invisible wave of energy slams into the upper atmosphere, it acts like a cosmic hammer shattering a pane of glass. The stable, life-giving molecules of nitrogen and oxygen that make up our air are torn apart. Electrons are stripped from their atomic nuclei, creating a cascade of ionization that disrupts global communications as effectively as any solar flare. But it does something far more insidious. The shattered atoms of nitrogen and oxygen immediately begin to recombine, but not into the benevolent air we breathe. They form vast planet-spanning clouds of nitrogen oxides, particularly nitrogen dioxide or NO2. This is the same acrid, poisonous chemical that gives urban smog its distinctive murky brown colour. Within minutes of the initial flash, the brilliant blue sky of this world would curdle into a sickly reddish-brown haze, choking the globe from pole to pole. The sun, once a source of life, would be reduced to a dim, smudged orb, its light struggling to pierce the newly formed chemical shroud. This newly created smog is a planetary poison, but its most devastating effect is what it does to the world's most critical defense, the ozone layer. The delicate shield of O3 molecules, which for eons had absorbed the lethal ultraviolet radiation from the planet's own sun, is now under a relentless chemical assault. Nitrogen oxides are ruthlessly efficient catalysts for ozone destruction. A single molecule of nitrogen oxide can destroy thousands upon thousands of ozone molecules, and it does so without being consumed itself. The GRB hasn't just punched a hole in the ozone layer. It has injected a self-replicating poison that will dismantle it piece by piece from the inside out. Models suggest that a GRB within our own galactic neighbourhood could obliterate up to 70% of Earth's ozone layer globally, with localised pockets of near-total destruction reaching 90%. The process would take months, but it would be inexorable. The planet's sunscreen, built up over billions of years of photosynthesis, would be gone. The world would be left naked and exposed to the full unfiltered fury of its own star. As this atmospheric alchemy is underway, a second wave of destruction arrives. It's slower, but in many ways far more malevolent. The jet from a gamma-ray burst is not just made of light, it is also a flood of matter, protons, electrons and atomic nuclei accelerated to just shy of the speed of light. This is a cosmic ray storm of unimaginable intensity. While the initial gamma rays were stopped by the upper atmosphere, these high-energy particles penetrate much deeper, peppering the entire atmospheric column with radioactive buckshot. As these cosmic rays strike air molecules, they create a shower of secondary particles, a ghostly rain of subatomic shrapnel. Among the most dangerous of these are muons. Muons are like heavier, more brutish cousins of the electron, and they are extraordinarily penetrating. They can travel through several meters of rock or water before being stopped. For any life that survived the initial flash by being on the night side of the planet or by hiding deep underground or underwater, the war for survival now enters a new silent phase. This moonshower would be a global phenomenon, raining down continuously for weeks or even months. It would be invisible, tasteless, odourless. It would pass through flesh and bone as if they were smoke. But with every particle that passes, it leaves a trail of damaged cells and shredded DNA. Mutation rates would skyrocket. Cancers would become rampant. For complex life, it would be a slow, agonizing death by 1,000 tiny invisible cuts. Aquatic ecosystems thought to be a safe harbour would be devastated. The muons would pierce the upper 100 metres of the ocean, with ease irradiating the plankton, coral reefs, and shallow water fish that form the foundation of the marine food web. The base of the planet's ecological pyramid would be systematically eroded, not with a bang, but with a persistent, inescapable whisper of radiation. Now, with the planet's defences shattered and its biosphere irradiated, the long-term climate catastrophe begins. Two horrifying possibilities emerge, and scientists are still debating which would be worse. The nitrogen dioxide smog now blanketing the globe is opaque. It blocks a significant portion of incoming sunlight. This would trigger a sudden and dramatic global cooling, an event known as a cosmic winter. Temperatures would plummet across the globe. Ice sheets would begin to expand rapidly from the poles, grinding over continents. The growing seasons would collapse, leading to a catastrophic failure of any remaining plant life. The planet, already reeling, would be plunged into a deep freeze that could last for decades, even centuries. But there is a second, more paradoxical outcome. While the smog blocks visible light, it can also act as a powerful greenhouse gas trapping infrared radiation heat that tries to escape from the planet's surface. It's possible that after an initial cooling period, the planet could be tipped into a runaway greenhouse effect. Temperatures would soar, boiling the oceans and turning the world into a sterile high-pressure cooker, a toxic sibling to the planet Venus. Global winter, or global furnace, a chilling choice. It's the ultimate cosmic cruelty. You not only die, you don't even get to know precisely how. The very mechanisms of your planet's climate, which once nurtured life, would be turned into an engine of extinction. The full ecological collapse would be a cascade. The phytoplankton in the oceans, responsible for a huge portion of the planet's oxygen, would be wiped out by the combination of the muon radiation and the intense solar UV now flooding the surface waters. As they die, the food chain collapses from the bottom up. The death of plants on land from the cold and the radiation would starve the herbivores. The carnivores would follow soon after. The mass extinction would be unlike any other. It would be swift, global, and indiscriminate, affecting life on land, in the sea, and in the air with brutal impartiality. When the dust finally settles centuries or millennia later, the world would be unrecognizable. It would be a ghost of its former self, perhaps, with only the hardiest microbes deep underground, or near hydrothermal vents surviving to tell the tale. A vibrant living world erased from the cosmic record by a flicker of light from a long-dead star. This scenario is so terrifying, so absolute, that it feels like science fiction. But we must ask the question, has this planetary execution ever actually happened? Has our own world ever found itself staring down the barrel of a cosmic gun? The fossil record of Earth is a book written in stone, and it tells a story of 5 great chapters of death, the 5 major mass extinctions. For most of these, we have compelling culprits, asteroid impacts, colossal volcanic activity. But one has always remained more mysterious. It is the Ordovician-Silurian extinction, which occurred around 450 million years ago. It was the second most severe extinction in Earth's history, wiping out an estimated 85% of all marine species. The evidence for what happened is strange. The extinction event was incredibly rapid, and it seemed to hit surface-dwelling and shallow water creatures like trilobites, brachiopods, and graptolites far harder than deep-water species. This is precisely what you would expect from a catastrophe that originated from the sky. Following the initial pulse of extinction, the geological record shows clear evidence of a sudden, intense, and short-lived ice age. Glaciers advanced across the supercontinent of Gondwana, causing sea levels to plummet before retreating again. A rapid death from above followed by a global winter. The kill signature matches the predictions of a gamma-ray burst with unnerving accuracy. We can't be certain, of course. The smoking gun, the specific dead star responsible, would be a white dwarf or a black hole, now its identity lost to the passage of 500 million years. But the hypothesis remains terrifyingly plausible. It suggests that our planet may have already suffered a glancing blow or a near miss from one of these cosmic assassins. The deep history of our world may contain a warning, a fossilized echo of a time when the sky fell. The life that survived the deep-sea creatures that hid from the light became the ancestors of much of the life we see today, including eventually our own. We may be the descendants of the survivors of a forgotten apocalypse. This realization changes our perception of the universe. We see it not just as a place of wonder and beauty, but as a place of profound and arbitrary violence. We are living in a cosmic shooting gallery where the weapons are invisible and the bullets travel at the speed of light. The silence and stability of our night sky are not a guarantee of safety, but perhaps just a testament to our incredible dumb luck. We've established the threat. We've dissected the kill chain from the first searing flash of gamma rays to the long, cold night of the cosmic winter. We've seen the ghostly fingerprints of such an event in the bedrock of our own planet. The evidence is in. The danger is real. The only questions left to answer are the ones that truly matter for our future. What are the odds? How often do these celestial rifles fire in our direction? And is there one somewhere out there in the darkness already taking aim? And so we arrive at the question that has been looming in the darkness, a whispered fear at the heart of this entire cosmic journey. The question that gives our story its name. Knowing what we now know about these celestial assassins, these engines of annihilation roaring in the distant deep, can you outrun a gamma-ray burst? The answer is simple, unequivocal, and profoundly terrifying. No, there is no race to be run. There is no contest to be had. To even frame it as a competition is to misunderstand the fundamental, unbreakable laws of the universe. It is a fiction we tell ourselves, a comforting delusion, that our ingenuity or speed could ever matter in the face of such absolute power. Imagine you are standing on a planet, our planet, and across the gulf of 30,000 light-years, a collapser's core has finally surrendered. The hypernova ignites a final failed scream against gravity. and from its heart the jet is born aimed directly at you. You might think you have time, 30,000 years an eternity for civilizations to rise and fall. But the light from that explosion, the visual warning, the brilliant new star appearing in our sky, is travelling toward us at the maximum speed the universe allows, the cosmic speed limit, the speed of light. And what are the gamma rays in that lethal beam travelling at precisely the same speed? The warning and the executioner arrive together. They are one and the same. There is no advance notice. There is no headline, no siren, no frantic call to action. The first moment you could ever possibly know that a gamma ray burst was coming is the exact same moment its energies are tearing you and everything you have ever known into constituent atoms. It is the ultimate ambush predator of the cosmos. You don't see the bullet coming, you don't even hear the shot. The first sign of danger is the impact itself, an impact that erases the very concept of you. But perhaps you argue we could be cleverer than that. Science has shown us that some particles might offer a fleeting head start. Neutrinos. Those ghostly, nearly massless particles we saw born in the heart of the collapsing star. They interact so weakly with matter that they escape the stellar core moments before the electromagnetic radiation, before the photons of light and gamma rays are freed. They pour through the collapsing star's outer layers as if they were nothing but empty space. So in theory, a sufficiently advanced neutrino detector on Earth could register a massive spike of them coming from a single point. It would be our only possible alarm bell, a silent, invisible tremor in the fabric of space-time heralding the apocalypse that follows on its heels. For a moment, a sliver of hope, an early warning. But how early? For a hypernova in our own galaxy, that warning might be a few minutes, perhaps an hour at most, depending on the progenitor star's structure. What could we possibly do with minutes? What grand evacuation plan could humanity enact in the time it takes to brew a pot of coffee? There is no ship fast enough. There is no bunker deep enough. We could not even broadcast a coherent planet-wide warning before the main event arrived. Humanity would die in ignorance and confusion, the vast majority never knowing why the sky suddenly caught fire. The neutrino signal is not a lifeline. It is a courtesy, a final, fleeting whisper from the universe letting a handful of scientists know that the end has come. It is the universe ringing the doorbell just as the house is vaporized. So let us dispense with the fantasy of escape. Let us confront the terrible reality of what would happen at the moment of arrival. The stopwatch begins now. Time 0. Across half the planet, the dayside hemisphere, facing the burst, the sky ceases to be the sky. In less than a millisecond, the prompt emission hits. A torrent of high-energy gamma-ray photons, a celestial fusillade of unimaginable intensity, slams into the upper atmosphere. It carries more energy in a few seconds than our sun will radiate over its entire 10 billion-year lifespan, all focused into a narrow, devastating beam. This is not light as we understand it. This is a force of pure, brutal dissolution. The air itself becomes the target. Each gamma-ray photon is a tiny, energetic bullet. When it strikes a molecule of nitrogen or oxygen, it triggers a cataclysmic chain reaction. The photon's energy is so immense it rips electrons away from their atoms, ionizing them, creating a cascade of charged particles. The atmosphere becomes a superheated plasma, glowing expanding shell of its former self. On the ground you would see the sky flash with a light so impossibly brilliant it would defy description, a blue-white incandescence that would instantly and permanently destroy the retinas of any creature facing it. But you would not have time to register the light, because in that same fraction of a second the radiation dose arrives. We measure radiation exposure in units called sieverts. A dose of 10 sieverts is invariably fatal to a human. A nuclear bomb's immediate fallout might deliver that and more. A gamma ray burst from across the galaxy would deliver to every square centimetre of the exposed hemisphere a dose of hundreds of thousands of sieverts. It is a number so far beyond lethal that the word loses all meaning. It is not a poison, it is an act of erasure. The gamma rays and the secondary particles they create, muons, pions, would shred the molecular structure of any living thing. DNA would not be merely damaged, it would be violently unzipped, shattered into incoherent fragments. Proteins would denature instantly. Cell walls would rupture. The complex, delicate chemistry of life would be pulverized. death would be so instantaneous that the brain synapses would not have time to fire a final signal of pain or fear. It would be a transition from existence to non-existence in a single, silent, radiant flash. Everything on the surface, every plant, every animal, every human being caught in the light of that terrible new star would be sterilized. The very soil cooked. The ocean's surface layers boiled. The dayside of Earth would become in a heartbeat a monument to cosmic violence, a sterile and silent rock. But the burst lasts for seconds, perhaps a minute, and then the prompt emission, the gamma-ray torrent, is over. The silence that follows is not one of peace. It is the silence of a world that has just received a mortal wound and is only now beginning to comprehend the damage. For the other half of the world, the night side, the initial blast would have been shielded by the planet itself. They would see a terrifying light show on the horizon, an aurora of impossible intensity wrapping around the globe. They would be alive, but their world and their future would be gone. The GRB's work of destruction has only just begun. The immense energy dumped into the atmosphere triggers a form of perverse planetary-scale alchemy. Our air, the very medium of our breath, is 78% nitrogen and 21% oxygen. Normally these two elements coexist peacefully, but under the brutalizing glare of the gamma rays, their stable diatomic bonds are shattered. Nitrogen N2 and oxygen O2 molecules are torn apart into highly reactive single atoms, and in the superheated chaos of the upper atmosphere, they recombine into something new. Something toxic. Nitrogen oxides, nitric oxide, and most devastatingly nitrogen dioxide, NO2. Ton upon ton of this poisonous brown gas is synthesized, billions of tons in a matter of minutes. The sky on the dayside, once a brilliant lethal white, now darkens into a murky reddish-brown haze, a planetary smog of our own atmosphere's making. This smog begins to spread, carried by the stratospheric winds, wrapping the entire globe in a toxic shroud. And this newly forged chemical has a voracious appetite. It seeks out and destroys one of the most vital components of our planet's life support system, the ozone layer. Ozone, a molecule made of 3 oxygen atoms, forms a delicate, fragile shield in our stratosphere, absorbing the most harmful ultraviolet radiation from our own sun. It is the only reason complex life on land was able to evolve. But the nitrogen oxides produced by the GRB act as a powerful catalyst, ripping ozone molecules apart with terrifying efficiency. One single molecule of nitrogen oxide can destroy thousands of ozone molecules before it is finally removed. The GRB has just flooded the upper atmosphere with trillions of them. The effect is not a thinning of the ozone layer like our past struggles with CFCs. It is an almost complete catastrophic annihilation. Within hours to days on the hemisphere that face the burst, the ozone shield is estimated to be destroyed by over 90%. Globally, as the nitrogen oxides circulate, the layer is reduced by more than half. The Earth is stripped naked before its own star. The sun, once the source of all life and warmth, becomes an enemy. Its unfiltered ultraviolet radiation, particularly UVB, pours down onto the planet's surface with sterilizing intensity. For the survivors on the night side, the rising of the sun would no longer signal a new day. It would signal a new kind of death. This intense UV radiation is a powerful mutagen. It sears through living tissue, causing catastrophic cell damage. Any surviving humans or animals who venture into the daylight would suffer severe burns within minutes. Blindness would become rampant. Cancers would bloom in the bodies of all who are exposed, but the most profound damage happens where we cannot see it in the foundation of the entire global food web. In the oceans, the phytoplankton, the microscopic marine algae that form the base of nearly all aquatic life, are obliterated. These organisms, which live in the sunlit upper layers of the water, have no defense against this level of UV radiation. They are bleached and killed on a global scale. With their death, the entire marine ecosystem collapses. The chain of life is severed at its first and most crucial link. Fish whales, seals, seabirds, everything that depends directly or indirectly on that phytoplankton foundation is now condemned to starvation. The oceans, which make up over 70% of our world, begin to die, and the sky continues to darken. The reddish-brown nitrogen dioxide smog is not just a sign of poison, it is a veil. It is highly effective at blocking visible sunlight, As this pall spreads around the planet, it chokes off the light that reaches the surface. This triggers a secondary cataclysm. On land, the surviving plants already struggling with UV damage are now starved of the light they need for photosynthesis. Global agriculture collapses entirely. The world's crops wither and die in the fields. Forests sicken. The planet's green lungs begin to fail, and with the sunlight blocked, global temperatures plummet. The smog acts as an anti-greenhouse, preventing the sun's warmth from reaching the ground. The planet is plunged into a rapid and severe ice age, a cosmic winter far more extreme than any nuclear winter we have ever modelled. The average global temperature could drop by 10, even 15 degrees Celsius in the span of a few years. Glaciers would begin a relentless advance from the poles. The growing seasons that no longer exist would be replaced by winters that never end. Humanity's few scattered survivors would face a world that is simultaneously being irradiated by UV, starving from a collapsed food chain and freezing to death. And still the universe is not finished with us. There is one final insult to add to this planetary injury. The nitrogen oxides in the atmosphere, the same chemicals that destroyed the ozone and blocked the sun, eventually mix with water vapour in the clouds. When they do, they form nitric acid. And this acid falls as rain. Not for a day or a week, but for years. The oceans already dying become more acidic, making it impossible for shell-forming creatures to survive. The soils on land are poisoned, their delicate pH balance destroyed. Freshwater sources become corrosive. The very rain, the symbol of life and renewal, now becomes another vector of death, a final chemical scourge upon a broken world. This is the legacy of a gamma-ray burst. It is not a single clean moment of destruction. It is a methodical, cascading planetary systems failure. It attacks the atmosphere, the climate, the chemistry of the oceans, and the biological foundation of life all at once. It is an event so thoroughly devastating that it resets the game of evolution back to zero. Perhaps in the deepest oceans near hydrothermal vents, some extremophile bacteria might survive. Perhaps buried miles beneath the ice or rock, some microbial life would endure the long winter. But for complex life for us, for the world as we have built it, and the biosphere as it has revolved over 500 million years, it is the end. No escape, no shelter, no hope of recovery. Just the stark, humbling reality of our own cosmic fragility. We are adrift in an ocean of unimaginable power, living through a quiet moment between storms. And we have learned that should one of those storms ever turn its gaze upon us, our story, and the story of our world, would end not with a bang, but with a flash of silent, impossible light. An epilogue of poison rain, and a long, encroaching cold. The sheer unanswerable finality of it all forces us to confront an even more profound question. If the universe is so adept at sterilization, so filled with these cataclysmic events, then why is there any life at all? And so we are left here on our small blue world, staring into the abyss. We have faced the physics of annihilation, peered into the heart of a dying star, and listened to the gravitational death scream of merging neutron stars. The question that launched our journey, a question of speed and survival, now seems almost naive. It was never truly about outrunning the blast. It was about understanding the bullet. A bullet made of pure energy travelling at the ultimate speed limit, fired from a gun of incomprehensible scale, across distances that mock our imagination. The answer was always no. You cannot outrun a gamma-ray burst. You can only hope the universe isn't pointing its weapon in your direction. Our journey to this humbling realization began not in the gleaming halls of a modern observatory, but in the tense, paranoid corridors of the Cold War. A secret vigil kept by the Vela satellites searching for the telltale flashes of clandestine nuclear tests on Earth. Instead, they found something far more powerful. Ghostly, fleeting signatures of immense energy coming from nowhere and everywhere at once. These were signals without a source, cosmic crimes without a culprit. For decades they remained the ultimate astronomical mystery, brief, enigmatic postcards from the edge of catastrophe. We knew they were violent, but we could not fathom their nature. They were smudges on our photographic plates, spikes on our readouts, maddeningly transient apparitions that vanished before our telescopes could fix their gaze. The universe was whispering of its true power, and for a long time we simply lacked the language to understand. That language began to form with the Compton Gamma Ray Observatory and its burst and transient source experiment BeppoSAX. For 9 years it patiently mapped the sky, collecting these whispers one by one, and the map it drew revealed a profound truth. The flashes were not clustered in the plane of our Milky Way, as they would be if they were local phenomena. They were isotropic, sprinkled evenly across the entire celestial sphere. This could only mean one thing: their origin was profoundly, unimaginably distant. They were not events happening in our galactic neighbourhood. They were cataclysms from the farthest reaches of space and time. This realization transformed the problem entirely. To be visible from billions of light years away, these bursts had to unleash a torrent of energy that beggared belief, and output that could for a few terrifying seconds outshine the combined light of every star in a million galaxies like our own. The mystery of their location was solved, but it had given birth to a far more frightening one. What kind of celestial engine could possibly generate such power? The lock was finally picked by an Italian-Dutch satellite named BeppoSAX. Its genius was its speed. It could catch the initial violent gamma-ray flash, and in mere moments pivot its X-ray telescopes to the same spot. It was there, in the fading, cooling embers of the explosion, that we found the key. The afterglow, a lingering, decaying echo of the main event, visible in X-rays, then in optical light, and finally in radio waves. For the first time we had a persistent source, glowing crime scene that we could study for weeks, even months. This afterglow allowed us to pinpoint the burst's location with unprecedented accuracy, fixing it not just in a patch of sky, but within the faint, fuzzy confines of a distant host galaxy. We could finally see where the monsters lived. They resided in the chaotic star-forming nurseries of young, turbulent galaxies, places teeming with the massive, short-lived stars capable of orchestrating such a demise. With a location and a source, the theoretical models, once speculative, began to crystallize into a terrifyingly clear picture. We had not discovered one monster, but two. The first, the engine behind the long-duration bursts, was the collapser. The final agonizing moments of a truly colossal star, a star dozens of times more massive than our Sun, which has exhausted its nuclear fuel. In its death, throws the core collapses under its own immense gravity, not into a neutron star, but past it into the ultimate abyss of a black hole. As this newborn black hole spins, it twists the magnetic fields of the dying star into a furious, wound-up dynamo. The surrounding stellar material raining down onto the event horizon is superheated into a swirling accretion disk, a cosmic drain of plasma screaming at millions of degrees. From the poles of this chaotic engine, the black hole launches two tightly focused opposing jets of matter and energy. These jets, travelling at over 99.9% the speed of light, are the celestial blowtorches we'd been searching for. They punch their way out from the star's collapsing outer layers in a journey that takes mere seconds, erupting into interstellar space as a focused beam of pure gamma radiation. The star itself is not just exploding, it is being violently and precisely dissected from the inside out by its own collapsed heart. Then, through a completely different line of inquiry, another monster was revealed. For years we had detected short-duration bursts, flashes lasting less than 2 seconds. They were too brief, their energy profile too distinct to be born from a collapsing star. Their origin remained elusive until a new window onto the cosmos was opened, not with light but with gravity itself. The Laser Interferometer, Gravitational Wave Observatory LIGO, and its European counterpart Virgo gave us the ability to hear the universe. And on August 17, 2017, they heard something spectacular. The sound of 2 neutron stars, the ultra-dense corpses of smaller suns, spiralling into one another after a gravitational dance that had lasted for eons. They had been orbiting each other for billions of years, but in their final moments they merged in a collision of unimaginable violence. A collision that rang the very fabric of space-time like a bell. Just 1.7 seconds after that gravitational chirp reached Earth, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the exact same region of the sky. The puzzle was solved. This was the kilonova. The merger didn't just forge a torrent of heavy elements like gold and platinum seeding the cosmos with treasure. It also created a volatile, short-lived hypermassive neutron star, or a black hole, which powered another briefer but no less ferocious jet of gamma rays. We now understand that the universe has 2 preferred methods for creating these beams of destruction. one powered by the birth of a black hole in the heart of a giant star, the other by the violent marriage of two stellar ghosts. Both produce the same terrifying result, a tightly collimated jet of lethal radiation. This beaming is both a blessing and a curse. It means that for every GRB we see, there are hundreds, perhaps thousands more, that we miss their lighthouse beams sweeping past us unseen and unfelt. The universe is filled with these silent, sweeping searchlights of doom. Our relative safety is a simple matter of geometric chance, a cosmic lottery of alignment. But if our ticket is ever called, if that beam were to sweep across our solar system, the consequences are stark and unforgiving. The primary danger isn't a kinetic blast wave like a conventional bomb. It's a silent, invisible flood of high-energy photons. The first indication would be a blinding flash in the sky, brighter than the sun even from thousands of light years away. But the true damage would be done long before our eyes could even register the light. The gamma rays would slam into our upper atmosphere, initiating a cascade of complex chemical reactions. They would rip nitrogen and oxygen molecules apart, breaking the fundamental bonds that hold our air together. These fractured molecules would then reform into vast clouds of nitrogen oxides. This reddish-brown smog would engulf the planet, blocking a significant portion of sunlight, potentially triggering a rapid and catastrophic drop in global temperatures, a cosmic winter. Simultaneously and more insidiously, these newly formed nitrogen compounds would catalytically destroy the ozone layer. Within weeks, the delicate shield that protects all surface life from the sun's harsh ultraviolet radiation would be stripped away perhaps by as much as 70% globally. The aftermath would be a planet under siege from two directions. From above, a relentless rain of hard UV radiation, sterilizing the surface of the land and the upper layers of the oceans. It would shred the DNA of any living thing it touched, causing catastrophic rates of cancer and mutation in surviving organisms and wiping out the plankton that form the very foundation of the marine food web. From below the acid rain, the nitrogen oxides would mix with water vapor in the atmosphere, falling back to Earth as nitric acid poisoning soils, lakes and rivers. Life on Earth would face a multi-pronged globe-spanning extinction event. It would not be a singular explosive end, but a slow, agonizing decline into a sterilized world. It is a chilling thought that some of the great extinction events in Earth's deep past, those mass dyings, recorded in the fossil record for which we have no clear terrestrial cause, could have been the faint long-range echo of a distant GRB. We may carry the scars of these cosmic encounters in our very evolutionary history, ghosts of past apocalypses written into the story of life itself. And yet our quest to understand these phenomena continues, driven by an insatiable curiosity that seems to defy the very terror they inspire. Our modern sentinels, the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope, continue. The vigil started by Vela, but with far greater power and precision. Swift is a rapid response artist, a marvel of celestial robotics. It detects a burst and within a minute autonomously reorients its entire spacecraft to bring its X-ray and UV optical telescopes to bear on the afterglow. It sends alerts to a global network of astronomers who scramble to point ground-based telescopes at the fading light, capturing data across the entire electromagnetic spectrum before it vanishes forever. Fermi, on the other hand, is a wide-eyed surveyor. Its large-area telescope sweeps the entire sky every 3 hours, building the most detailed high-energy map of the universe ever created, catching the most energetic photons from the most violent bursts, pushing the very limits of what our theories can explain. Together, they're filling in the details of the picture, showing us GRBs from the dawn of time, revealing subtle variations in their light curves and finding strange outliers that challenge our neat categories of long and short. They have found bursts that seem to lack a supernova, and others with bizarrely extended X-ray flares, suggesting that the central engine doesn't simply die, but sputters and coughs for hours or even days after the main event. Every new observation adds a new layer of complexity, a new wrinkle to the story. We thought we had found the monsters, but we are beginning to realize we have only glimpsed the first few species in a vast and varied cosmic ecosystem of cataclysm. The next great leap forward is happening right now in the era of multi-messenger astronomy. The synchronized detection of gravitational waves and a short GRB in 2017 was not an end but a beginning. It was the Rosetta Stone event that proved our models correct and opened a new chapter. With gravitational wave detectors, we no longer just see the flash of the cannon, we can feel the recoil. We can hear the space-time vibrations of the merging stars, giving us a direct, untainted measurement of the masses involved, their spin, and the mind-boggling energies released in their final moments. By combining this gravitational information with the light captured by telescopes like Swift Fermi, and soon the James Webb Space Telescope, we can perform a complete autopsy on a cosmic explosion from billions of light-years away. We can probe the fundamental physics of matter at densities impossible to create on Earth, testing the limits of Einstein's theory of general relativity in the most extreme environments the universe can conjure. We are moving beyond merely cataloguing the events to performing intricate remote celestial engineering, reverse engineering the engines of cosmic death. This ongoing quest forces us to confront our own existence in a profoundly new way. We look out at the velvet blackness studded with the serene twinkling lights of distant suns, and we see a celestial panorama of breathtaking beauty and tranquility. But we now know this tranquility is an illusion. It is a snapshot, a single frame in a movie filled with unimaginable violence. The universe is not a peaceful garden. It is a shooting gallery, and our planet is a fragile moving target. The silence of space is punctuated by these gamma-ray shouts, a constant random drumbeat of obliteration happening somewhere in the cosmos at least once a day. The Fermi paradox, the eerie question of where is everybody, finds a potential and terrifying answer in this realization. Perhaps the great filter. The barrier that prevents intelligent life from becoming a multiplanetary starfaring civilization isn't a single event. Perhaps it's a recurring statistical certainty. Perhaps the galaxy is periodically sterilized by the jets of its own dying stars, resetting the evolutionary clock over and over again. Maybe life is not rare because it is hard to start, but because it is so incredibly easy to extinguish. Living with this knowledge is a uniquely human challenge. It is the ultimate expression of the Copernican principle. Not only are we not at the center of the universe, but we also inhabit a cosmos that is fundamentally indifferent and often hostile to our existence. Our lives, our history, our art, our conflicts, our triumphs, all of it unfolds on a delicate membrane of biology, stretched precariously over a rock, vulnerable to a stray beam of light from a galaxy we have never seen. There is a cosmic loneliness in that thought, a sense of profound and humbling fragility. The persistence of life on Earth for nearly 4 billion years feels less like a given and more like an astonishing, improbable winning streak against breathtaking odds. We are the descendants of an unbroken chain of survivors on a planet that has so far dodged the universe's deadliest bullets. But this knowledge does not lead us to despair. Instead, it seems to fuel our ambition. It imbues our search for understanding with a sense of urgency and profound importance. We are the one species we know of on this planet that has been able to look up to build the tools to decipher the light from these cataclysms and to understand the threat. Our science is not merely an academic exercise, it is the ultimate act of self-awareness. It is the universe through us becoming conscious of its own terrifying power. We continue to build our observatories, our gravitational wave detectors, our space telescopes, pointing them like shields of knowledge at the great violent dark. We do this because it is in our nature. We are the creatures who huddle around a fire telling stories about the monsters that lurk in the night. Now the night is the cosmos itself, and the monsters are real, so we are left here beneath a sky that will forever look different to us now. It is a tapestry, woven with threads of both creation and destruction, a place of serene beauty and latent fury. We are ephemeral, a fleeting consciousness in an ocean of deep time, our existence, a delicate frost on a window pane, beautiful but transient. The question of whether we can outrun a gamma-ray burst has been answered. We cannot. But our journey has revealed a deeper, more meaningful question. What will we do with the time we have in the brief, precious interval of cosmic calm we are lucky enough to inhabit? Our answer is to keep looking up, to keep listening, to keep questioning. To face the immensity and the danger not with fear, but with an indomitable curiosity. And in that relentless, courageous search for understanding, we find our own small, defiant way to stare back into the brilliant, terrifying light.